Welcome to the second part of organic chemistry. So in the first video, we did an introduction to what organic chemistry is all about. We also talked about different families. In this video, we're going to start a discussion on one of the families called alkanes. So remember, for family in this topic, we're going to be using the word homologous series. You understand what that means. Once we get done with this homologous series, we're going to move to the next homologous series, which is called alkenes. Then we'll proceed to alcohols, carboxylic acids and esters, and then we'll end with polymers. So in this specific video, where we're going to do some sort of homologo about alkenes, we are going to it's going to be a bit lengthy. Maybe we're going to consume about 20 to 30 minutes, so just make sure that you are prepared for the ride. Let's get started. Alkanes. So we're going to start with a term that you might be familiar with, which is saturated. We're going to start with the other name for alkanes, which is called saturated hydrocarbons. What does it mean? So I want you to think about this as we're discussing. We have encountered this word saturated in saturated solution, which is a solution which cannot dissolve any more solute, no matter how you stir, it won't, because it has enough solutes already. So in those lines, think about what a saturated hydrocarbons might be. As you are thinking, I will continue reminding you of what we discussed in the introduction. So the general molecular formula for alkanes is CnH2n plus 2, where n can be any integer, like 1, 2, 3, 4, just like that, starting from 1 in short. So n cannot be 0, it has to be 1 going up. So for example, if our n is 1 here, it means we have 1 carbon atom. Then hydrogen atoms, we just do 2 times n plus 2, where if n is 1, it will be 2 times 1 plus 2. 2 times 1 is 2 plus 2 is going to be 4. So this is going to be CH4. So all alkanes are represented by this formula. Then their functional group is a single carbon-to-carbon covalent bonds. All alkanes have a single bond between their carbon atoms. Now, why are they called saturated hydrocarbons? They are called saturated hydrocarbons because they have the required or maximum number of hydrogen atoms. In short, the carbon atoms, the maximum number of bonds that a normal carbon atom can form are 4 bonds. Let me say that again. The maximum number of bonds a carbon atom can form is 4. Okay, so for alkanes, all the carbon atoms have 4 bonds, meaning that all of their bonds are occupied either by hydrogen atoms or carbon atoms. So what I'm trying to say is this: we can have this carbon atom, it will have these 4 bonds, and on each of the bonds there's going to be a hydrogen or a carbon atom, mostly hydrogen atoms. Okay, so this is what it means. All the bonds, or all the possible bonds, or the maximum bonds are they have hydrogen atoms, or sometimes it can be carbon atoms. For example, we can have a carbon atom here, another carbon atom here, and they can be connected by this bond. Then the remaining 3 bonds can be occupied by hydrogen. It can also happen that we can have other than this carbon atom, we can have another carbon atom here, such that this carbon here is connected to this carbon here and connected to this carbon here, but the remaining 2 are going to have hydrogen. So it's all about having the maximum possible number of hydrogen atoms around carbon atoms. That's what it means by saturated hydrocarbons. So they all end with the suffix ANE. So here are some examples of alkanes. So in this field here, in this column, we have alkanes. Here we have molecular formulas. Here we've got their structural formulas. Here we have what is called a condensed formula. What is a condensed formula? You're going to understand as we are just discussing each of the groups. Each of the examples. So we're going to start with methane. So this is methane. The prefix meth means one, meaning that it has one carbon atom. So to write the molecular formula for methane, you get this prefix meth. Then you go to the suffix n, which means it belongs to alkanes. Alkanes have a formula CnH2n plus 2. So if you write your formula CnH2n plus 2, your n, they have said meth is 1, so your n is 1. So here it will be 1. Then H2n plus 2, where there's n, you put 1, you're going to have 4. Meaning that you're going to have 1 and you're going to have 4. That's why we have this. Here there's an invisible 1. The structural formula for methane is this: carbon occupied by the 4 hydrogen atoms, since we have only one carbon atom. Then the condensed formula in this case looks exactly like the molecular formula, but as you see, as we keep on going through the examples, the condensed formula, you see its importance. The next is ethane. So ethane, eth is 2. Okay, so 2 carbon atoms. So if you follow the formula 2n plus 2, it will be 2 times 2, 4 plus 2. It will give you 6 hydrogen atoms. Now, to write the structural formula, there are 2 carbon atoms. So you start with the 2 carbon atoms. You write one carbon atom single bonded to another carbon atom. Then the rest of the bonds, you put hydrogen. You populate them with hydrogen. Okay. Now the condensed formula will give you an idea into how the various atoms are connected as compared to the molecular formula. The molecular formula just gives you the number and types of atoms in a compound. Like there are 2 types of atoms, carbon and hydrogen. There are 2 carbons and 6 hydrogens. Well, the condensed formula shows you that there is a carbon atom surrounded by 3 hydrogen atoms, bonded to another carbon atom surrounded by 3 hydrogen atoms, as you can see here. The next is propane. So propane, the molecular formula is C3H8, since prop means 3. So if you use the formula, you're going to get 8 here. The structural formula, again, you start with carbon atoms. So there are 3 carbon atoms. You write carbon atoms, you connect them with single bonds, then you populate the remaining of the bonds with hydrogen atoms. Keep in mind that each carbon atom should have 4 bonds. So for example, for this carbon atom, at first it will be connected to this carbon atom and to this carbon atom, meaning that there are 2 remaining. So you can put 1 here and the other 1 here. But for this one, which is connected to 1 carbon atom, it needs 3. So you're going to give it the 3. The condensed formula is going to be CH3, CH2, CH3, which is this. I've written it like this because I don't have space, but it's supposed to be in the same line: CH3, CH2, CH3. Butane, the same applies, and of course the structure formula is just CH3, CH2, CH2, CH3. The condensed formula will just be like the way I've said it: CH3, CH2, CH2, CH3. But this CH2, since it's repeating, to avoid wastage of space and time, we just write it in this form: CH3, open bracket, CH2, close bracket, and a 2 outside, then CH. This 2 shows that there are 2 CH2s. So this is CH3, space here. Then finally pentane, just like that. So we go to preparation of methane. How do we prepare methane? So why are we talking about methane? Why are we not talking about pentane or hexane? The reason is simple. If you remember in the introduction, we said members of the homologous series or homologies have similar methods of preparing. Okay, so because they have similar methods of preparing, it means the method used to prepare methane is just the same as the method that can be used to prepare butane, pentane, and the likes. So methane can be prepared by heating a mixture of 2 substances, one being anhydrous sodium ethanoate, which is written like this, and soda lime, which is sodium hydroxide. So soda lime is the trivial or the common name of sodium hydroxide. So there are some compounds which have common names. like we are used to call them in a certain way, but of course in chemistry they're supposed to be called in the way that we can even understand the various radicals and atoms that makes them up. So sodium hydroxide, as we know it in chemistry, its common name or trivial name is soda lime, which is, of course, we know the chemical formula there. So now what happens, the reaction is this. Sodium ethanoate, these are supposed to be connected here, sorry. So sodium ethanoate reacts with sodium hydroxide to produce methane and sodium carbonate. The apparatus for this reaction is this. So sodium ethanoate and sodium hydroxide are heated. The sodium carbonate that's going to be formed is a solid, so it will remain here. Well, the methane, it's a gas, it's going to evaporate, and it's going to be delivered by the delivery tube to here. Let me say that again. I said it's going to evaporate. It can only evaporate if it was a liquid that turned into a gas. So once the reaction occurs, there will be a gas, and the gas will naturally go, is going to be delivered to this side by the delivery tube. Physical properties of alkanes. So concerning physical properties of alkanes, we're not going to maybe state specific physical properties because they don't have the same physical properties. What they have are some sort of trends, like periodic trends. Remember what used to happen on the periodic table? As you go down the group, something happens. As you go up the group, something happens. So the same trend is observed among alkanes. The underlying principle is that as the number of carbon atoms increases, alkanes tend to become more solid. So in short, the smaller the number of carbon atoms, the more the behavior is like gases, and the greater the number of carbon atoms, the more the behavior is like solids. And you're going to see the physical properties. We expect solids to have a higher melting points than liquid than gases. So the same trend you're going to see. We also expect solids to have a greater density than liquids than gases. So even alkanes, that's the same trend that they have. So in short, their physical states vary at room temperature and pressure. Lower members, those with a small number of carbon atoms such as methane and ethane, are gases. Then as the number of carbon atoms keeps on increasing, they become liquids. And as you go higher, they become solids. Their melting and boiling points increases as the carbon chain increases. Something that you should expect on a trend that gets more solid when the number of carbon atoms increases. So we expect the melting point and boiling point to increase as the carbon chain increases. Their densities also increase as the carbon chain increases. We go to chemical properties of alkanes. So the way we're going to discuss chemical properties is we're going to take a look at some examples of reactions where alkanes participate and the expected products. So when you're studying these things, you have to know the types of reactions and the types of products, so that in an exam, if they ask you to write an equation, you know that if an alkane reacts with this, these are the expected products. That's how to go about it. The first is combustion. There are two types of combustion. There's complete combustion and incomplete combustion. This is not the first time we're talking about combustion, and this combustion is not any different from the combustion we have been studying in pollution and others. We talked about complete combustion, which occurs when there's enough oxygen in a reaction, and in such a reaction, carbon dioxide is one of the products. With that being said, in a plentiful supply of air, alkanes react with oxygen to form carbon dioxide and water. Here's an example. We have this alkane, it reacts with oxygen and produces carbon dioxide and water. So just as a quick exercise, what alkane is this? So it has 2 carbon atoms. 2, the prefix for 2 is eth, so this is ethane. So, but the main point from here is carbon dioxide is produced and water. Then in incomplete combustion, or in a very limited supply of air, alkanes react with oxygen to form carbon and water. Sometimes carbon monoxide and water. So here is an example. We have this alkane reacting with oxygen to form carbon and water. So note that sometimes carbon monoxide is produced, sometimes it can be carbon monoxide and water. The other type of reaction where we see our alkanes having fun is substitution reaction. Again, this is not the first time we're meeting this substitution reaction. We did substitution reaction when we were studying acids and bases. Also, I think periodic table there was some sort of a substitution reaction. Just like in football, substitution involves someone being replaced by someone else. So a substitution reaction is a reaction in which one atom or group of atoms in a molecule is replaced by another. Alkanes undergo substitution reactions with halogens in the presence of ultraviolet light. So ultraviolet light is also found in sunlight. This ultraviolet light acts as a catalyst. It speeds up the process. So whenever you have an alkane and a halogen is a group 7 element such as chlorine, fluorine, bromine. So these group 7 elements in the presence of alkanes, and if there is ultraviolet light, there is a substitution reaction that occurs. Here's an example. The example is where methane is involved and the process is called halogenation of methane. So methane can react with chlorine gas in the presence of sunlight to form what is called chloromethane and hydrogen chloride. This hydrogen chloride is hydrochloric acid, but when it is in gaseous state. So this is called halogenation of methane, like I've said. This is the formula. This is the equation. So of methane reacting with chlorine to produce chloromethane and hydrogen chloride. To understand what's happening here, let me just give you a bit of an insight. You can see that there are 4 hydrogen atoms here. So these 4 hydrogen atoms, after the reaction, there are 3, and there's chlorine, meaning that one has been replaced by this chlorine. That one which has been replaced has gone to combine with the other atom that was here to make hydrogen chloride. Let's use structure formula to understand fully. So using structure formula, we have the methane reacting with chlorine. So this chlorine goes here and this hydrogen comes here. So we have this structure and we have this. So for this to happen, these are the conditions that are needed. First, the temperature should be about 200 degrees Celsius. Then the catalyst is sunlight, which provides ultraviolet light. Now we go to near the last parts of this part of organic chemistry. I know it's a lot to digest, and here it's going to get a little bit funny because we're going to learn a new skill, and that is how to name organic compounds. To be specific, saturated hydrocarbons, alkanes. So we're going to learn about a concept called isomerism of alkanes. Isomerism is the existence of compounds with the same molecular formula but different structural formula. What does this mean? If you write the molecular formula, the molecular formula is going to be the same, but if you draw the structure, they're going to be different. So this is isomerism. Such compounds are called isomers of each other. So isomers are compounds which have the same molecular formula but different structural formula, just for those who like mastering definitions. Alkanes with more than 3 carbon atoms exhibit isomerism. So methane does not exhibit isomerism. Ethane does not exhibit, but after that, propane going upwards, that is more than 3 carbon atoms, we see some isomerism, as you're going to see. So what we're going to learn is how to name isomers. Isomers can have the same molecular formula, different structure formulas, and also they can have different names. Why is that they have different names? It's because the name gives us an insight into its structure. There is always a normal one and the one now that has funny structures, which we need to give some name. So there are two, or there are going to be two or more than two. The first one is the normal one, like for example, hexane. We can have a normal hexane, then we're going to have an isomer of hexane that's going to have a different name. So the standard that is used to name hydrocarbons that exhibit isomerism is called the International Union for Pure and Applied Chemistry, UPAC. So the rules for naming alkanes, I'm going to teach you with examples. So I've got this alkane. Who can name this alkane? I wish it was a physical class so that I can be pointing. With that being said, naming this alkane is simple because this, we just count the number of carbon atoms, since we know that the homologous series is alkane. So 1, 2, 3, 4. So therefore 4 is but. So this is a normal butane. So the formula is C4H10 normal butane. So whenever it is like this is normal, so that becomes the name. But this can also be written in a different way, such that the molecular formula is going to be the same, but the structure is going to be different. We can write something like this. So if you look at this, how many carbon atoms are here? 1, 2, 3, 4. 4 carbon atoms, which means this is the molecular formula. How many hydrogen atoms? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogen atoms. Mean that this and this are isomers because they have the same molecular formula, but the structure formula are different. So the name of this is also going to be different. So there are some rules that you have to learn on naming this. So the first is identify the longest chain of carbon atoms. So in this compound, there are two chains of carbon atoms. Chains are just one carbon atom that is connected to another. The first chain is 1, 2, 3. The second chain is 1, 2. Okay, there's another chain here, but maybe I won't show you because it might be a bit outside the scope. But there are two chains, 1, 2, 3 and 1, 2. So which one is long? So this one is the longest. It has 3 carbon atoms, while this one has 2. So this one is the one that's going to carry more like the name of this, as you are going to see. So this has 3, which means it's a pentane. Okay, that's the first step. The second step is you have to identify the methyl group. What is a methyl group? A methyl group is a CH3 group, a group made of 1 carbon atom and 3 hydrogen atoms. In this case, we have this carbon and these 3. So this is a methyl group. So the methyl group, it's here. It can be anywhere. If we are chosen this to be our chain, this can be taken to be a methyl group and this can be taken to be a methyl group. But since we have chosen this, since it is the longest chain, this is our methyl group. So once you have identified your methyl group, you have to name the carbon atoms in the longest chain. So these carbon atoms, you need to give them names. So start from 1 going up. But which one do you start with? You can either start with this or this. But to choose, you choose the one where the methyl group is close to. In this case, it is in between. So you can choose this to start. You can start with this or you can start with this. If the methyl group was here, we could have started with this since the methyl group is here. But since the methyl group is here, so we can start with this or we can start with this. Again, if the methyl group was here, we could have started with this. So we choose, we name carbon atoms starting with the one that's going to give us the smallest number. Okay, let me just rephrase that. I don't want to take you into confusion. So, like I have said, just take what I've said, name the carbon atoms, in such a way that you start with the one that where the methyl group is close to. So you look at the both ends of the chain, you look at the position of the methyl group, you ask yourself, which side is it? Is it this side or the other side? Here or here? So if the methyl group is close to this side, you start with this. If the methyl group is close to this side, you start with this. If it is on the middle, you start with any. In this case, we're going to start with this one just by choice. So you name them. So this, by the way, we're going to write the name here. So this is carbon 1, this is carbon 2, this is carbon 3. So we ask ourselves, where is the methyl group among these three? So it is on carbon 2. So the name is going to be, the name usually starts with the number of the carbon atom. So it's going to be 2. Then we're going to have this group, which is methyl. So it's going to be 2 methyl. Then now the longest chain, 2 methyl propane, 2 methyl propane. Okay. So between the number and the group, this methyl group, you put a dash. I've said a lot of things, so let me just write down. So the molecular formula we've agreed. Then the name is going to be 2-methyl propane. Propane because there are 3. If you have been given this name and you have been asked to draw the structure formula, first start with this prop, meaning that you're going to have the longest chain with 3 carbon atoms. Then on carbon number 2, you're going to have a methyl group. So you can choose which one you want to be 2. You can start with this one or this one. So if you start with this one, for example, this is going to be 1, then this one is going to be 2. Then you draw a methyl group. Or if you want, you can start with this one. Then here it's going to be 2, draw a methyl group. Okay, hope that is sinking. So let's take a look at another example, which is going to be a bit complicated, but the same 3 rules apply. I'm just going to introduce maybe 1 or 2 key points to keep in mind. What about this? See, so this one is a straight one, so we count 1, 2, 3, 4, 5. So it's 5, which means it's pentane. Okay, so what if we have this? So this one, which one? First thing, identify the longest chain. 1, 2, no? 1, 2, 3, 4. So this is the longest chain. 4 is butane. So mean that the name is going to be butane. So what is it that we should put on the left of the name? So first, we look at the methyl group. It's here. Okay. So this methyl group is connected to this carbon atom. So which one should we start with when naming? This carbon atom or this carbon atom? Of course, the methyl group is close to this carbon atom. So this is going to be carbon atom 1. So 1, this is going to be 2, this is going to be 3, this is going to be 4. So this carbon atom 1, okay, so we go to carbon atom 2. There was no need for me to say carbon atom 1. Okay, so we go to carbon atom 2. So mean that on carbon 2, we have a methyl group. So it's going to be 2-methyl butane. As simple as that. And of course, the molecular formula is the same, C5H12. It can also have another isomer. The same butane can have another isomer. This and this are the same. They have the same molecular formula, C5H12. As you can see, there are 5 carbon atoms and 12 hydrogen atoms. So what name can we give this? This is the third isomer among these compounds that have this isomerism. So again, the first thing, longest chain. So if you look, we have 1, 2, 3 carbon atoms. Again here, 1, 2, 3. So you can choose any because they are all 3. So you can choose this or you can choose this. So I'll just choose the normal one that we're used to. So again, naming, since it is in between, so you can start with this or this. Again, I'll start with the one that we're used to from left. So it's 1, 2, 3. But don't get deceived that always you have to start here. You can start even this side. So 1, 2, 3. So on 2, now we have a methyl group and a methyl group. Now I think you can see the inside of this structure. So we have a methyl group here and another methyl group here. So we have 2 methyl groups. Okay, but since this is the longest chain, it has 3. So we know that it's going to be the prefix for the main name is going to have 3, which is prop. So it's going to be a propane. Now, for the left-hand side, what we're going to put on the left-hand side of the name, it's these methyls. So how do we show that there are 2 methyls? So if there are 2 methyls, we use the word di. We put di as a prefix to methyl so that it becomes dimethyl. So it's dimethyl, it means there are 2 methyl. If there were 3, it could have been tri. Okay? So what I'm saying is, if there are 2 groups, we use di. If there are 3 groups, use tri. Dimethyl or trimethyl. With that being said, how do we show that they are all here? Simple. We just write the numbers where they are. So this one is on 2 and this one is on 2. So we're going to say 2. The numbers are separated by commas. So that's another thing you should keep in mind. The key points that I'd said that I'll introduce is di and tri, that you put as a prefix to the name. And also, if the groups are on more than 1 carbon atom, like here, okay, they are on this carbon atom, but there are 2 groups. How do you show their positions? So you just have to write the numbers of the number of the carbon atoms where they are. You separate the numbers. If there are more than 1 number, you separate them by commas. So this compound, it's 2, since this is on 2 and this is on 2, so it's 2, since there are 2, dimethyl. Then the main chain, it's propane, so it's going to be 2 dimethyl propane. The 2 are going to be separated by commas, and between the numbers and the methyl we put a line. So it's going to be 2,2-dimethyl propane. That's the name. And again, the molecular formula is just the same, no difference. So to finish now, since we've dealt with hard stuffs, so let's look at simple stuffs. So now another chemical property of alkanes is they undergo a process called cracking. So cracking of alkanes. Cracking is just the breakdown of large hydrocarbon molecule into simple and smaller molecules. Alkanes break down to produce sometimes alkenes, sometimes they produce short chain alkanes, and in some cases hydrogen gas. So there are different types of cracking. Actually, there are just 2 types of cracking. The first one is thermocracking. So in thermocracking, heat is used to break down large molecules into smaller molecules. Example of thermocracking is this, where we have butane. After being heated, it breaks into this ethane. So C2, 2 times 2, 4, yes, it's ethane, plus this ethene, and this supposed to be plus here. And again, if you further heat this, you're going to have hydrogen and ethene. So we haven't talked about the alkenes, so I don't want to go into details about alkenes. We haven't talked about them, but just know this is an alkene. Okay, not alkane, but alkene. Okay, and then we have hydrogen here. Next, we go to catalytic cracking, the other type of cracking. So this is where both heat and a catalyst are used to break down large molecules into smaller ones. So common catalysts that are used include aluminium oxide, silica, or silicon dioxide. These are the common catalysts that are used. Examples. So here we have an alkene with 17 carbon atoms. So this alkene, when there is a proper catalyst and it is heated, it breaks down into an alkene. Sorry, this is an alkane. This is an alkane. So when you heat it, it breaks down into an alkene. How do I tell it's an alkene? Because the general formula of alkene is CnH2n. So C2H4. Okay, and it also produces another alkane and another alkene. Okay, for those who don't understand how to differentiate, you will as we go into the next topic. So, condition for cracking. For this example, the catalyst is aluminum oxide, the temperature is 600 degrees Celsius. What are the importance of cracking? First, it is used in the production of raw materials for petrochemicals like ethane and hydrogen. Second, it is used in the production of petrol. We end this topic with fuels. So a fuel is a substance which burns in air to form or to produce useful energy. Where do we get fuel? Normally, fuel is we get it from there are different sources, but one of the major sources are natural gas. So the main component of natural gas is methane. Sometimes when they just say natural gas, you just have to know it's methane. If you remember in the preparation of hydrogen, we talked about how hydrogen is prepared using steam and natural gas. Natural gas is methane. So natural gas is usually mined and purified before use. The other source is petroleum, which is also called crude oil. So crude oil is a mixture of long chain hydrocarbons and some elements like sulfur and nitrogen. So in the last part of this discussion, we are going to study how crude oil is separated. Crude means mixed. So when they say crude oil, you can relate it to oil that has different types of oils or different types of hydrocarbons in it. So these hydrocarbons have to be separated. Common examples of hydrocarbons are paraffin, which is called kerosene, of course, even diesel itself. So to separate kerosene and diesel, because normally in crude oil they are all together, so they have to be separated, and that's what we're going to take a look at as we conclude this topic. So the method of separation that is used, or the method that is used to refine crude oil is called fractional distillation, which we're already familiar with. So this is the fractionating column of crude oil. Okay, so hot crude oil is pumped here. Once it is pumped, then the mixture is going to be, since it's hot, so there will be that continuous heating and there will be evaporation. So what happens is different components of crude oil are going to separate according to different boiling points. It turns out that this apparatus, the way it is designed, the one that is volatile, or the one that has a smaller boiling point, evaporates. Okay, that we know, evaporates first, but it is collected on top here. So petroleum gas has the lowest boiling point, which by now you should know that it is somehow married to the number of carbon atoms in petroleum, meaning that petroleum has less carbon atoms as compared to petrol. Petrol has slightly a higher boiling point and separates second. After petrol, kerosene follows, then diesel oil, then lubricating oil, then fuel oil, then paraffin waxes, then bitumen. So bitumen has the highest boiling point. So the various components of crude oil and the possible number of carbon chains they have, and also some uses as we conclude. So petroleum gas has different hydrocarbons having carbon atoms from carbon atom 1 to carbon atom 4. In short, it has hydrocarbons that have they are different. We can have methane in petroleum gas, which has one carbon atom. We can have ethane, we can have propane, we can have butane, C1 to C4, meaning that hydrocarbons that have one carbon atom to hydrocarbons that have 4 carbon atoms are present in petroleum gas. So it is used in camping stoves and cookers as bottled gas. Then petrol, which is also called gasoline, is used as a fuel in internal combustion engines in vehicles. Then we have kerosene, which has C10 to C17. It is used as a fuel in jets, used in paraffin lamps for lighting, also used in paraffin lamps for cooking. Then we have diesel oil, which is also called gas. It is used as a fuel in diesel engines like trains, hammer mills, tractors, and lorries. Then we also have lubricating oil, which is usually used as a lubricant in machines to reduce friction. Then we have fuel oil, which is used as a fuel in ships, power stations, and industrial machinery. Then of course we have paraffin waxes, which is used in making waxes, polishes, and wax paper. Then finally bitumen, that one with the highest boiling point, used to tar roads, used as roofing material. So when they are making a tarmac, that sticky substance, that's bitumen. We have consumed 40 minutes. I'd planned that maybe to be 30 minutes, but it's 40. And we are going to end Alkanes here. Hope you forgive me. I had planned to deliver this topic or this part of the topic into 2 videos, but I thought you guys can handle it. Happy solving.